Okay, so for this example, we're going to look at a spring mass equation that actually has damping taking effect. So we want to first recall our equation from before, which of course is m times y double prime plus b times y prime plus k times y is equal to 0. Once again, these problems are unforced. The next example will be forced. So the mass in this problem is 0.5. So 0.5 times y prime plus our damping constant, which they tell us is 4 Newton seconds per meter. So that's a 4 times y prime. And then the spring constant, we call the stiffness, is going to be plus 10 times y is equal to 0. So again, we're going to put our mass in the front. We put the damping constant in the middle, and then we put the stiffness constant at the end of the equation. The next thing for us to do is put this in more of a standard form to make it easier to solve. So let's multiply the whole equation through by 2 to clear out the decimals. So in doing so, we're going to have a y double prime plus 8 times y prime plus 20 times y is equal to 0. The auxiliary equation for this is r squared plus 8 times r plus 20 is equal to 0. And you'll notice very quickly that this equation does not factor, so instead we choose the quadratic formula, or completing the square. We'll complete the square because it has a nice even coefficient in the middle. So that's going to be r squared plus 8r, and if we take half of 8, which is 4, and square it, that's going to make adding 16 to both sides. And of course that is equal to the negative 20 that we brought over plus 16. So that's going to give us an r plus 4. Quantity squared is equal to a negative 4. So r plus 4 equals plus or minus 2i. When we take square root to both sides, I guess we could draw that over top. And so then r is equal to a negative 4 plus or minus 2 times I. So our general solution, our y of t, is going to have arbitrary constant c1 e to the negative 4t times the cosine of 2t plus a c2 e to the negative 4t times the sine of 2t. We also have two initial conditions that we need to gather from the problem. So the first one, it says that the mass is moved 2 meters to the left of equilibrium. So that tells us that the initial position of the spring mass is going to be negative 2 meters. And then it also says that we have our initial rightward velocity of 1 meter per second. So that tells us that y prime is equal to a positive 1, because again, that motion is towards the right. So now we can go in and find our values of c1 and c2. For starters, we know that y of 0, which is negative 2, will be a c1 e to the 0 cosine 0 plus c2 e to the 0 sine of 0. That second term, of course, drops out. Cosine of 0 and e of 0 is 1, so that makes c1 equal to a negative 2. In the next video, we could probably just find the video here. So let's just, it's the coefficient here. So we'll just scroll up. And now let's find y prime. Y prime of t requires product rule. That's going to be a negative 4 c1 e to the negative 4t times the cosine of 2t plus c1 e to the negative 4t times a negative 2 sine of 2t, and then plus a negative 4 c2 e to the negative 4t sine of 2t, and that's going to be then plus a c2 e to the negative 4t times 2 cosine of 2t. And we know again that y prime of 0 must equal 1. So that means that 1 will be equal to this expression evaluated at 0. So we're going to have a negative 4c1 from the first term. The second term drops out because it's got the sign of 0. The third term drops out, sign of 0 again. And then the last term is going to be 2c2. All right, so we have negative 4c1 plus 2c2 equals 1. We can substitute in our value of c1. So 1 is equal to negative 4 times a negative 2 plus 2c2. So that means that 1 is equal to 8 plus 2 times c2. Negative 7 equals 2c2. So c2 is negative 7 halves. So in our next video, we'll put these constants together with our solution, and we'll have our solution to the initial value problem that we can then study.